Kirchhoff's rules. Up until this point, we've been analyzing simple circuits by combining resistors in series and parallel and using Ohm's law. This works for simple circuits, but in order to analyze more complex circuits, we need to use Kirchhoff's rules, which are based on the laws of conservation of charge and energy. Kirchhoff's first rule, or the junction rule, is based on the law of conservation of charge. It states, at any junction point marked here by a dot, the sum of all currents entering the junction point must equal the sum of all the currents exiting the junction. For example, the current here in I1 plus the current here in I2 is going to equal the current in I3. The junction rule makes sense since all of the charges are going to follow one branch or the other. There's nowhere else for the charges to go. Here are some examples of the junction rule in action. Let's say we have current going this way and then splitting up. That means that all of this current is either going to go this way or that way. So therefore the sum of those currents have to be equal to I1. Over here we have current coming down this way and then splitting up that way and that way, which means I1 plus I3 must equal I2. Here's an example of the junction rule in action. To find the current through the entire circuit, so that would be like I1 over here. It would also be over here. So here we have I1. We first need to find the equivalent resistance for the circuit. So these two resistors are in parallel, and we know that because there is a junction here where the current splits. So we're going to use our parallel resistor equation, 4 ohms and 6 ohms, so 1 over 4 plus 1 over 6. We get a common denominator, add them together, flip it over, and we get an equivalent resistance of 2.4 ohms. Next, let's find I1, the current coming from the battery. So I1 here is going to be V over R, that's Ohm's law. The voltage is the voltage of the battery, and the resistance here will be the resistance of the entire circuit, which we already found to be 2.4 ohms. Therefore, the current leaving the battery is 0.83 amps. Just make sure to use the voltage from the battery and the resistance of the entire circuit when we're trying to find the total current going through the circuit. Now let's find I2, the current going up this branch. Due to Kirchhoff's junction rule, we know that I2 must be less than I1. How do we know this? Well, I1 is the total current in the circuit, while I2 is just the current going through one branch. The current splits up into two branches right here at this junction. So how much of the current is going through the 4 ohm resistor versus the 6 ohm resistor, and that would be I3 going this way? Let's find out. These resistors are set up in parallel. Therefore, they must have the same voltage drops, right? So a charge is either going to go this way or it's going to go all the way around. But either way, it has to use up all 2 volts of its energy in either resistor. So therefore, the voltage drops are 2 volts for each of those resistors. So we can plug in information into Ohm's law about each resistor, or about each branch. So here, I2, we go through 2 volts of voltage here. That's how much we drop in that branch. And the total resistance of that branch is 4 ohms. So therefore, 0.5 amps of the 0.83 amps go this way. That means the rest of the current goes to the right here. But we could just plug in information into Ohm's law about the I3 branch, right? The voltage is 2 volts again, but the resistance is 6 ohms. So that gives us 0.33 amps. Do these two currents add up to the total current? Yes, they do. Kirchhoff's second rule, or the loop rule, is based on the law of conservation of energy. It states, the sum of all changes in electric potential, or voltage, around any closed path must equal 0. For example, the sum of the voltage drops here is equal to the voltage across the battery. So if this is V, that means that we leave with V voltage. We're going to lose V1 here. We will lose the rest of the energy there, which means this voltage drop plus that voltage drop must equal the voltage from the battery. Here's a very simple example with numbers. The battery provides 9 volts of electric potential. 2 of those volts are used up in the first resistor. The last 7 of those volts are used up in the second resistor. Algebraically, there are 2 ways to think about it. This number here must be equal to that number plus that number, so 9 volts equals 2 plus 7. Another way to think about it is that if you go this way across this battery, that's like positive 9 volts. When you then use up 2 volts here, that's like negative 2 volts. Then you use up 7 volts there, that's like minus 7 volts, and those add up to 0. You might be wondering why we need to go over something that seems so simple in so much detail. The loop rule will be necessary when dealing with complicated circuits, where current is flowing in unknown directions, or if there are multiple batteries. Here's an example of a circuit that would require using this rule carefully. When problem solving with Kirchhoff's rules, the first step is to draw an expected direction of the current for each circuit element. The direction doesn't matter. If it turns out the real direction is in the opposite direction, you'll just get a negative value for the current. The second step is to apply the junction rule to each junction. You need as many equations as there are unknowns. You can also use Ohm's law to reduce the number of unknowns. Next, apply the loop rule for each loop. Draw a loop and sum up the voltages in the loop to equal 0. So here, we just have one loop, so it's pretty simple. If, while traversing a loop, you go through a resistor in the same direction as the current, apply a negative sign to the voltage. So what that means is that if we're going this way, this is our loop, we're going this way, we're passing through this resistor in the same direction of the current as what we assume the current's going that way, then this voltage will be negative. So V1 will be negative. Then we're going to go through resistor 2, so V2 will also be negative since the current is in the same direction as the loop. If the battery here is going to be positive if you leave the positive terminal. So if you're going through the battery and you leave the positive side, that will be a positive voltage. So that's why this V is positive. All right, and so here we have the voltage drop across resistor 1. We can replace that with Ohm's law. Remember, V equals IR. So therefore, we have I1 R1 and I2 R2. Finally, you just solve these equations algebraically. Let's work through an example together. Find the unknown currents, voltages, and resistances in the following circuit. So here we have one battery, and we have, several paths going around. We have a couple different loops. First, we're going to draw an expected direction of current. So we're going to say, all right, here's our battery. Our current will leave the battery. Let's say it goes this way around like that. Some of it will go that way. Remember, if we're wrong, we'll just get a negative value for current, which is how we'll know that it's actually the other way. Next, we're going to apply the junction rule to each junction. Remember, we're going to need as many equations as there are unknowns. So junction 1 is here. So I1 has to equal I2 plus I4, because if the current's going this way, it's going to split up into those two branches there. We have another junction here, and we have current coming in this way and that way. So I4 plus I2 has to be equal to I3. All right, next we're going to apply the loop rule for each loop. We're going to start with these two loops here. If we need a third loop, we can always draw a loop that goes all the way around as well. But let's start here. So in this loop, we have R3 here, we have R1, and R4. So as we go around this way, we're going in the direction of current. So going through this resistor, we're going in the direction of current, therefore this voltage drop, V3, will be negative. V1 will also be negative because we're going in the direction of current, and V4 through R4 here is also negative. Then we can go ahead and replace those V's with IRs because that's Ohm's law, and all three terms are negative and they add up to 0. Next, moving over to this loop, we're going through the battery, out through the positive side. Therefore, this voltage will be positive. Now, as you can see, we're going this way, but the current is going the other way. So therefore, this voltage drop will also be positive. Then we go through this resistor in the direction of current. Therefore, this voltage drop is negative. And that completes our loop, add up to 0. So here we replace this voltage drop with IR, and we replace that voltage drop with IR, and we move on to our next step. All right, now it's time to solve the equations algebraically. So here are all of our equations. From the junction rule, we had this equation and this equation. And so we can plug in values, right? So what is the current through I2? It's 2.6 amps. So we can put 2.6 in there. We don't know I4 yet, but we can put 2.6 in there as well. We also have our two loop rule equations. And so we know that I3 times R3 must be 1.7. We'll see how we went from V to IR, but then we went right back to V. So I guess we didn't have to do that conversion. But that's our voltage drop. Here we know I1. We know R1, but not I1. So R1 is 5. So we have 5 I1. And here we know R4 is 2. It's covered up there, but it is 2. So we have 2 times I4. We plug in that 2 for R4 here. Over here, what do we know? We know the battery is 12. Does not say it there, but we did have that on the first slide. 12. Then we know that R4 is 2, so we plug the 2 in there. And we know that, what do we see? I2 is this one. We know 2.6 times 3. So here's the math. We can figure out, we can just plug those numbers in. 3 times 2.6 is 7.8. And here you can see the math for that equals 0. So now we have we have 4 equations. We've plugged in everything we know. All right, so at this point we have 4 equations and only 3 unknowns. So we can solve for I1, I3, and I4. At this point, it's a matter of practice and insight. Look at equation L2. We can solve this for I4. So, because this is a number and that's a number. So I4 is negative 2.1 amps. Negative, well, all that tells us is that we were wrong about the direction of current here. It actually goes that way. If we plug that value into equation L1, we can find I1, because then we have all numbers and just one unknown, and it becomes 0.5 amps. We can then use this equation to find I3, which is also 0.5 amps. And that makes sense because they're in the same branch right here, so you should get the same current for I3 and I1. A table is a great way to keep track of your work. The givens are in red ink, so this is what we were given at the beginning of the problem. We've now found all the currents, and we put in V2. So we found this, and this, and that. We put them in the table. Now it's just a matter of using Ohm's law to fill out the rest of the table. Here is the completed table for this problem. Find the unknowns in the following circuit. The complete solution is shown on the next slide. Hint, you don't necessarily need Kirchhoff's rules, just circuit knowledge and Ohm's law. All right, let's solve this together. I'm going to solve it without Kirchhoff's rules. I want to figure out the total current leaving the battery. So first, I need to know the equivalent resistance of the circuit. Over here, we have 2 resistors in series, which means that they're kind of just like one resistor that has a resistance of 5 ohms. Over here, we don't know the resistances, but we do know the current. So this, I'll call this I1, that's 7. And this one will be I2, and that is 3, which means the total current must be 3 plus 7. Because that's how much went that way is 7, that much that way, 3 amps went that way, therefore 10 amps must have left the battery. So we now know that the total current in the circuit is 10 amps. We know Oh, and look, it says right here that I3 is 10 amps, and that makes sense because that's how much current is going around this branch, which means that that's also I4 is 10 amps. Now we can use Ohm's law. So Ohm's law, V equals I, R. I is 10, R is 3. That means that 30 volts are dropped in this resistor of the 120. Over here we have 2 and 10. That means 20 volts are dropped. So 20 plus 30 is 50 volts. So 50 of the 120 are used up in this branch. Now these two resistors are in parallel, which means they have the same voltage drop. So let's say a charge left with 120 volts. It's going to use some of it here, and then it's going to use 50 of it there, or throughout both of them. So how much does it have to lose in just one of these resistors? Well, that would be 120 minus 50, which is 70. So the voltage drops are the same, 70 volts. Now we can use Ohm's law. So we're trying to find R. So Ohm's law is I equals V over R. Therefore, R equals V over I. V is 70. I is 7. Oh, that's easy. Resistance 10 ohms. Here we have 70 and 3. So R equals V over I. So V is 70. I is 3. I'm going to break out my calculator here. 70 divided by 3 is 23-ish. 23-ish ohms. And I think we solved it. All right, and here are all of the solutions, and we did it correctly. Let's look at a circuit that has more than one battery. So here we have a 9-volt battery and a 3-volt battery. So we will have to use Kirchhoff's loop rule here. We have 3 loops. Here, here, and all the way around. So let's use the loop rule. So, all right, we're going to say the current is going up this way and around. So through this battery, that's going to be positive 9. Then we're going to go through R1 in the direction of the current, so that will be negative. So the voltage drop across this resistor is I1, R1. And then we go this way in the direction of current, so that will also be negative, and it will be I2, R2 is the amount of voltage lost. Those have to add up to 0. In our second loop, we start by going through our battery this way, and that will be positive 3 volts. Then we go up against the direction of current. That's why this term is going to be positive, I2, R2. Then we go through R3 in the direction of the current. That's why it's negative. Those have to add up to 0. If we then go around the entire loop, and we're starting with the 3-volt battery, this will be positive 3 volts since we're leaving the positive terminal. Then we go through this battery, and it's also going through the positive terminal, so it's also positive. Then we're going to go in the direction of current through R1, so it's negative, and that's the voltage, IR. Then we go through the third resistor in the direction of current, so it's also negative. So that also has to add up to 0. Now in this example, we have actually flipped this battery around. So what changes? Well, anywhere we saw 3 volts before, now it's going to be negative. So that's the thing that changes if the battery flips around. Because if we go this way through the battery, we are now leaving the negative end of the battery. So then you put a negative sign in front of that voltage.